And I think we are good to go. So thanks everybody for coming to my talk on measurement and engineering of thermal radiation. I'm excited to be speaking to you from my apartment in Madison, Wisconsin. So my virtual background over here is the Unitarian Meeting House, which is an architectural landmark designed by Frank Lloyd Wright. And it's just a few minutes away from me whenever I go out on my walks. I also have my OSA lanyard here from a recent OSA conference because we couldn't get together in person for CLIO this time, but I'm trying to do my best to replicate the environment. So before I get started, I'd like to acknowledge a lot of folks that contributed to this work, including folks in my group at UW-Madison, as well as a lot of external collaborators, in particular at the University of Vienna, at Purdue, and at the Naval Research Laboratory. I'd like to highlight Dr. Yuzha Xiao, who's a postdoctoral scholar in my group and has done a lot of work to make everything I'm going to show you in this talk possible. And he also has a talk in just about 45 minutes. So please stick around for that. I'd also like to acknowledge financial support from a few funding agencies. We've been very well supported. We've been very fortunate to be supported by the Office of Naval Research, the National Science Foundation, and the Department of Energy for a lot of the work that I'm going to show you here today. So here's an outline for my talk. I'm going to give a refresher on thermal emission, what thermal emission is. I'm going to discuss precision thermal emission measurements under various challenging conditions. And then I'll discuss a few topics, including depth thermography, which is a new technique that we developed to measure temperature underneath surfaces of materials using thermal emission measurements. We'll discuss a little bit about some temperature tunable optical materials that are useful for thermal emission engineering, focusing on these complex oxides, vanadium dioxide and samarium nickel oxide. I'll show you how using one of these materials we can demonstrate a rather unique type of optical coating called a zero-differential thermal emitter, which emits the same amount of thermal radiation irrespective of temperature over a certain temperature range. And finally, I'll show you a recent result that we got, which is, I think, a world record for the temporal control of the thermal emissivity. All right. So first, a refresher on thermal radiation. So in general, every object emits thermal radiation, and the amount of thermal radiation that it emits depends on its temperature and also on its optical properties. So the spectral thermal radiation emitted by a blackbody is given by Planck's law, this guy over here, which can be integrated over wavelength and also over solid angle to yield the Stefan-Boltzmann law, which just relates the amount of thermally emitted power, the area, and temperature to the fourth. Where the temperature of the fourth is in Kelvin or other absolute units. So here you can see the distribution, the Planck distribution. This is spectral radiance in terms of wavelength. You can see that the hotter an object is, the more thermal radiation it gives off, and the more that thermal radiation spectrum is blue shifted. And then if you integrate that overall wavelength, you see that the irradiance or the total amount of emitted power increases as a function of temperature. And of course, this is in Celsius, but if this were in Kelvin, this would go as temperature of the fourth. So from this, we get some rather basic results that are very intuitive for folks, which is that hotter objects emit more light. So if you have a black body, the total amount of emitted power divided by area is just proportional to temperature to the fourth. If you have any real object, then for that object, we define a parameter called an emissivity, which is a number between 0 and 1 that tells you kind of the propensity of the object to emit. How likely is it to emit? And this number can be between 0 and 1 in kind of its integrated form, or it can be between 0 and 1 for the spectral emissivity, which depends on wavelength. So here's just a kind of an example of this. This is the blackbody radiance versus temperature. So the emissivity here is 1, but we're integrating here over all wavelengths and here over just subsets. And irrespective of which one of these you pick, you'll always see that the total amount of thermal radiation for a blackbody increases with temperature, which is to be expected. And this is the cornerstone, for example, of infrared imaging, where you have, say, a temperature distribution on an object, and you point an infrared camera on it, and you get out the thermal power, and there's kind of a one-to-one map between temperature and thermal emitted power. This is essentially the one-to-one map up here. So there's an opportunity here, which is to engineer thermal emission for a wide variety of applications. So the spectrum and intensity of thermal radiation emitted by an object is this Planck law multiplied by this emissivity, which is between 0 and 1, and it can be a function of many, many things. It can be a function of wavelength, it can be a function of direction, of polarization, temperature, applied field, and so forth. So you can really use that to engineer the emissivity. You can imagine thermal emitters that emit only in one direction, that emit only a narrow range of wavelengths, that emit only polarized light, and so forth and so forth. And usually the way that we think about engineering these things is actually by engineering the optical absorptivity as a function of these parameters, because according to a thermodynamic statement called Kirchhoff's law of thermal radiation, the emissivity, which is again a function of all these parameters, is precisely equal to the optical absorptivity. So this is very, very widely used, this Kirchhoff's law of thermal radiation. To get an understanding of what kind of things are possible when you engineer this emissivity parameter, I would recommend you check out a recent review article that we wrote with Andrea Alou's group that was published in Nature Materials last year. Okay, so one thing that's worth paying attention to here that I think is a little bit less known is that this emissivity can easily be kind of an undefined parameter or an ill-defined parameter. And that can happen under a number of circumstances, but broadly that happens when your object is not necessarily at thermal equilibrium. So that means that the object is made up of a bunch of little pieces that are all different temperatures, or maybe the electron temperature and the lattice temperature are different and so forth. And in all of these cases, this is not a well-defined parameter. You can't define the temperature very well, and therefore you can't define the emissivity very well either. And so for those cases, and even some cases where this does apply, there is a need for experimental capability to measure thermal emission, for example, the spectrum, the direction, and so forth, for a variety of applications in characterization and thermoregulation and infrared camouflage and so forth. So we spent quite a bit of time in our group over the last 4 or 5 years working on this. It sounds like a really simple problem. It sounds like you should just take your sample and stick it on a temperature controller and send the output to a spectrometer, which in our lab is an FTIR because we're working primarily in the infrared. And then you just capture the spectrum and call it a day. Maybe you change the angle of the sample using, for example, a rotation stage like this, and then you have all the information you need. However, what we found, and of course what has been known in the literature as well, is that this is very difficult to do, especially under certain circumstances. So your data analysis after you've done the experiment has to account for thermal emission from the detector, from the optics. It has to account for frequency-dependent response of the instrument, so kind of the responsivity of the detector, the transmission of the optics. It's not necessarily trivial to obtain and characterize a really good standard reference, which also may be dependent on temperature, and so that becomes a problem. So this is actually rather difficult to do. We spent a lot of time trying to calibrate our experimental measurements, taking care of things like thermal emission that's kind of background emission moving in the forward direction, background emission moving in the backward direction, which does some very funky things to the resulting spectrum if you kind of naively try to extract it. It's really not that easy to do, but when all is said and done, we can actually get very, very good thermal emission measurements. Just to give you an example, here is the emissivity at an angle of 10 degrees. This is unpolarized or mixed polarization as a function of wavelength for a fused silica wafer, which is kind of a common reference we like to use. And this is at rather low temperatures. I think this is at something like 40 degrees. I don't remember the exact value. And you can see that the emissivity that we extracted by kind of appropriately calibrating our instrument is really, really dead on to what you get when you do ellipsometry analysis, apply Kirchhoff's law, and you're very, very careful about how you do this. So the method that we developed can be used to precisely measure thermal emission from objects with temperature-dependent emissivities for cases when the emissivity is not defined and so forth. Kind of the beginnings of this are described in this Physical Review Applied Physical Review Applied article that came out in 2019. But later on, in kind of a follow-up article that's in archive right now and is currently in press and laser and photonics reviews, we actually wrote a rather big and long article that describes how to do this. And here's a flow chart from that article. So essentially, the flow chart asks you, what kind of thermal emission measurement do you want to do? Is your sample in equilibrium or not? Do you have a background that's negligible or not? That depends on, for example, the temperature of the emitter, the temperature of your background. Is your emissivity changing with temperature? And there's many different ways of how you might go about calibrating your system so that you get really, really good emissivity data from your measurement. However, we've kind of done the legwork now, and we think we're quite confident in our ability to do these kind of measurements. And if you'd like to do some of this as well, I recommend checking out this archive preprint, which will be published in Laser and Photonics Reviews soon. But for now, let me show you what this kind of measurement really enables. I should mention, before I forget, that just in about 35 minutes, Yuja is going to be giving a talk on exactly this topic, how you actually do these measurements. So please stick around to check that out. Okay, so here's one example of something that we've been able to do now that we have a very, very good, very precise, very accurate way of doing thermal emission measurements. One example is called something that we call depth thermography. So thermography is just the use of infrared cameras to measure temperature. And usually what you're measuring, or what you think you're measuring, is kind of a surface temperature with an infrared camera, the temperature on the surfaces of objects. Everything underneath is usually kind of hidden. Using this very precise method of measuring thermal emission spectra, we can in certain cases, for certain materials, peer underneath objects and try to measure the temperature kind of as a function of depth. So here's an example of how something like this might work. If you have an object which has a, let's say, a flat surface here, it doesn't necessarily have to be, and it has some loss which is a function of wavelength, then that affects, when you're doing a thermal emission measurement up here, the amount of loss versus wavelength affects where the thermal emission signal is coming from, right? So the thermal emission signal that's coming from the very, very top, all of it is going to make it to, at least that's emitted in the upward direction, is going to make it to your spectrometer, your infrared camera, and so forth. However, if you're looking at thermal emission kind of from deeper into the material, some of that light is going to be absorbed before it reaches the surface. And of course, these things are connected because also you have an amount of absorption that depends on wavelength as well. So this is kind of a complicated process, but essentially what you can do is you can take all that information, you can build a model, and you can try to retrieve the temperature as a function of depth as it actually was. So it's kind of a metrology or measurement technique. Here's an example of this. So what we did is we took kind of a heater stage, and on top of it, we put a test sample, which for us was, again, just a fused silica window. It's actually kind of a thick fused silica window that was about 1 millimeter thick. And we did a measurement where we measured the spectral radiance versus wavelength using our technique. We were very, very careful. And if you take a look, you find some interesting things that you might not expect to see. So if you look at the experiment, this is the experimental data, and you look at a model that we built, for example, if you just apply Kirchhoff's law and Planck's law with a kind of the known emissivity, you will find that the two curves match up really, really well, except for in this region over here at very, very short wavelengths, kind of between 5 and 6 microns, where the with this blue curve, this model deviates from the experiment. And you might look at this and you say, well, of course, I mean, this is just experimental error. Look, you can't even see it on the plot. I mean, you have to zoom all the way in to be able to see it. However, it turns out that this difference over here is actually quite meaningful, because in the region where you're at kind of 5 or 6 microns, the fused silica becomes semi-transparent. And so what you're seeing over here in the experiment, the reason why the spectral radiance is a little bit higher here than it is in our model, is because the region over here, closer to the heater, is hotter than the region on the surface, because the heat is coming from the bottom. And you're seeing some thermal emission from this region making it out, and therefore the spectrum is just a little bit larger over here than it would be otherwise. And so if we build a model to account for that, Yuja built a very serious model based on kind of fluctuation, dissipation physics, and a thin film, kind of a transfer matrix calculation to essentially figure out how much light is really emerging from each one of these layers and finally emerging and being detected. And we're able to fit this curve. Actually, I'm sorry, this is not a fit. This is just a calculation that accurately describes the experiment. And in this case, this match is really, really perfect. And because we're able to do that, we're then able to say, okay, given this spectrum, so given the spectrum without any information about the temperature, what is the temperature? And long story short, we are able to back out the temperature as a function of depth quite well, making certain assumptions. So right now, this requires very precise calibration, good signal to noise, both of which we have, but also it requires the knowledge of optical properties, which is potentially difficult, and you have to do some other measurements to be able to do that, though we think that this limitation can be overcome. And so again, I remind you to check out Yuja's talk to see more details about how this was done. Okay, so now I want to talk a little bit more about kind of engineering of thermal emission rather than sensing or metrology. So the spectrum of thermal radiation is kind of always given by this blackbody contribution multiplied by this emissivity, assuming that you can that your emitters are in equilibrium. And this emissivity, again, can depend on many different parameters. And one of those parameters, the one that we've been interested in our group for a while, is temperature. So it's quite interesting to engineer objects with temperature-dependent emissivity. So for example, the emissivity, which is equal to the absorptivity, depends on temperature in a way in which you now have two terms, this term and this term, that are both temperature-dependent. You can imagine some really strange behavior, such as you're increasing the temperature and your emissivity goes down so much that the overall thermal emission goes down. That's kind of a very strange situation. And so if you want to play these kind of games, if you want this temperature as an engineering knob in your toolbox of engineering thermal emission, you need materials with temperature tunable optical properties, and this temperature tunability needs to be very, very large, right? Because this blackbody contribution changes quite rapidly as a function of temperature, and therefore this emissivity also has to change quite rapidly. Otherwise, you can essentially neglect that temperature dependence. And so we in our group at UW-Madison and with many, many collaborators have been exploring the use of various materials which are very, very temperature tunable. Their optical properties depend very strongly on temperature. One such material that's quite well known at this point in the community is vanadium dioxide. Vanadium dioxide, or VO2, has been studied since something like 1960, in part because it has a very complex and very fascinating insulator-to-metal transition. So essentially, if you heat it up past about 70 degrees Celsius, it goes from a kind of insulating semiconducting state to a metallic state. The electrical properties change dramatically by something like the resistivity drops by something like 4 orders of magnitude, and the optical properties change a lot as well, especially in the infrared, because the Drude contribution from is kind of a dominant contribution to the optical properties of the material. And one thing that we kind of found surprising over the last several years is that even though this material has been known for, a very, very long time, for something like 60 years, and has been studied for optics for probably 20 or 30 or 40 years, there hasn't been really a very good, very detailed optical data set, like data set of N and K as a function of temperature, that enables a lot of electromagnetic simulations and design and so forth. And so we went out and did just that. So this is a result that was published last year by first author Cheng-Hao Wan from our group, and it shows the N and K of VO2 as a function of wavelength, as a function of temperature, all the way from the ultraviolet to the far infrared. So this is a very, very broad spectral range. And so if you take a look at this paper and you look at the supplementary, we included the full data set. You can copy and paste it in your simulations, and you can do VO2 simulations, pretty much at any optical frequency that you want. Another thing that we found digging into the literature is that every time you see a VO2 data set somewhere out in the literature, it's different. So if you pull up one paper, you get one data set. If you pull out another paper, you get another data set, and they don't agree at all. And so we wanted to really figure that out. And so we partnered with a number of folks at Purdue and Sherman Ramanathan's group at Physical Sciences Incorporated, and we synthesized VO2 in several different ways, several different thicknesses and different substrates using different techniques, and we characterized all of these materials, all of these thin films, from the UV to the far infrared as a function of temperature, and we found something quite interesting, that if you look at the far infrared, so kind of beyond about 11 microns, then pretty much whenever you deposit a new film, if you use a different substrate, or if you deposit a different thickness, or if you sputter versus you do sol-gel synthesis, your results are going to be quite different because of all of these optical phonon resonances over here that are very, very sensitive to the material, to how it's deposited. If you look over here below about 1 or 2 microns, so kind of in the near infrared and the visible, you'll see that every time you deposit a film, it's quite different because the electronic structure, the band structure, depends very strongly, again, on the deposition conditions. And so you really have to characterize your film every time before you do some simulations. However, there's this magic region between about 2 microns and about 11 microns, where pretty much every film is more or less the same, at least in the insulating phase, where these materials are also quite low loss and quite transparent. And so in this kind of magic mid-infrared range between about 2 and 11 microns, you can pretty much trust that no matter how you deposit your VO2, as long as it's reasonable quality VO2, like the stoichiometry is okay, it's at least somewhat polycrystalline, you are kind of expecting the optical properties to remain the same, and therefore you can actually use this full data set to do your optical design and trust that it's going to represent reality reasonably well. So we're quite excited about that finding. Long before we did this characterization, I did a study while I was still a graduate student at Harvard in Federico Capasso's group, showing that if you just deposit a layer of VO2 on sapphire, for example, you can observe this emitted power versus temperature. That's very, very strange. You have kind of this local maximum. You have this region where as the temperature increases, the amount of thermal emission decreases. We're quite excited about this for camouflage. We're excited about this for thermoregulation. It kind of conceals your temperature information from infrared cameras. For example, here at 60 degrees, the infrared camera sees kind of a hotter temperature than at 85 degrees, which is very, very counterintuitive. And so when I moved to UW-Madison in 2015, we were quite excited to get started on playing with other types of phase transition materials to do similar type of engineering of thermal radiation. And in particular, we focused kind of on the zoo of complex oxides with insulator-to-metal phase transitions that have been explored by our collaborators at Purdue and Sherm Ramanathan's group. For example, these nicolates, these vanadium oxides, and so forth. Each one of them that have transitions at quite different temperatures. So you can look at these temperatures and realize why VO2 is so commonly used is because the transition is very close to room temperature, which is quite nice. But we decided to take a look at this samarium nickel oxide, and we did this spectroscopic ellipsometry, now just in the mid-infrared, from 2 to 14 microns, observing this very large change in NK, but it's quite gradual, which we thought was going to be kind of an interesting material system for us. And so the goal that we had initially using this material system was to create a thermal emitter that has a many-to-one relationship between temperature and emitted power. So I mentioned at the very beginning of this talk that traditionally your temperature and power relationship is kind of a one-to-one relationship. The hotter an object is, the more light it gives off, and that's why infrared cameras can see a lot of information about the temperature of the environment. And we wanted to make like a many-to-one relationship where no matter what temperature you were at, the camera read the same thing, and therefore it's kind of a way of concealing information. So in other words, what we really needed is a thermal power versus temperature that instead of increasing like would be normally the case, it was kind of this zero differential case. The derivative was zero, and therefore you had a completely flat curve. And if you take a look at this equation, this integrated, essentially Stefan Boltzmann law, you can see that essentially your total emissivity needs to decrease as fast as temperature to the fourth increases to kind of cancel this out. Unfortunately, we were able to do this with a samarium nickel oxide film on top of an appropriate substrate with an appropriate thickness and so forth. This is the measured emissivity versus wavelength versus temperature. You can see it's this nice gradual decrease that matches the Planck distribution quite well. And so if you take a look at the radiance, kind of integrated overall wavelengths versus temperature, you can see that the blackbody is going to increase with temperature as expected, but the zero differential thermal emitter has a very constant curve. The slope is zero, and therefore, no matter kind of what temperature you're at within this maybe 100 to 135 degrees Celsius region, your radiance is the same. And so we did some experiments with infrared cameras to show this. They're kind of fun. So we took a sample, we mounted it with tape, Kapton tape on a heater. So there was kind of a temperature distribution here. If you have a typical sample, for example, this is a piece of sapphire, you see that it's hotter over here, colder over here, and there's a gradient. However, if you put in our zero differential thermal emitter, you see that there's no apparent gradient. There isn't a gradient in temperature, but you can't see it because there's also a gradient in emissivity that cancels out the gradient in temperature as far as the infrared camera is concerned. So it's kind of a fun result. So we were excited about this, for example, for kind of concealing infrared signatures for privacy applications and so forth. So this is kind of a mock-up infrared image of going from kind of a conventional, surface where you can see it's hotter in the middle than it is on the outside. This is a train car, and if the mock-up here is that if you put one of these coatings on top, you can kind of make everything look uniform, and you're concealing a lot of information. Okay, so the very last thing I want to show you is our results on on time modulation of emissivity. So before, we discussed that the emissivity could be a function of wavelength, could be a function of polarization, angle. I just showed you that it can be a function of temperature, and that can result in some very interesting demonstrations and applications. However, it can also be a function of time, right? You can change emissivity as a function of time, which is expected to change the total amount of thermal emission that is given off of your object. And so what we wanted to do in this work, which was published in Light Science and Applications in 2019, was to demonstrate the fastest ever modulation of thermal emissivity. And so the way that we did this is we took some samples, some semiconductors, we tested silicon, gallium arsenide. Here I'll show you the gallium arsenide result. It's just a wafer of gallium arsenide, nothing fancy. Gallium arsenide that's undoped usually has a very low emissivity because it's reasonably transparent in the mid-infrared. We excited it with a pump pulse. This was done using some high-power lasers at the Naval Research Lab in the group of Alberto Piquet, our collaborators. And this pump pulse temporarily excited a very very large number of free carriers, which changed the emissivity dramatically. And for that short amount of time, this sample became quite emissive. So there was kind of a thermal emitted pulse, and then those carriers recombined and went away, and the pulse was gone. And so this is the result. You can see that the power versus time, this is experimental for different fluences of the pump laser, and for the gallium arsenide at 20 degrees Celsius, you can see that there's this first pulse, and then there's this kind of long decay, and this pulse is on the order of a nanosecond. This decay is on the order of a few nanoseconds. So this is, as far as we understand, the fastest ever modulation of emissivity by something like a factor of 1,000. So we're quite excited about this result. It's also a rather unique method of infrared pulse generation from visible pulses. Okay, so I'm going to end on just showing you the outline, and I'm happy to take any questions. Thanks so much for participating in my talk at Virtual Clio. Cheers.